All right, welcome back everyone. Today is Wednesday. Okay, so looks like everybody turned in your homework and ready to take the quiz tomorrow. I'm going to post the solutions of all homework as soon as I go back to my office, so you can check it, everything. Okay. And then I realized there's a mistake, so I'm going to fix the mistakes before my my solutions are. Okay, so like I said, I'm a human. I may make mistakes, so please feel free to point it out if you feel that, hey, professor, you might be wrong. It is actually it is going to be appreciated. Okay. Okay. So today, what are we going to do? We are going to get into Unit 3B, trusses, frames, and machines. This is probably, I would safely say, if my memory a long time ago is correct, this is probably the most challenging subject. When I was a student taking this class, statics, I spent most of the time trusses. It's not difficult, it's just tons of work to figure out things. It's just applying equations of equilibrium at every single joint of the truss frame. If the truss is made up by 200 frames, you have to have 200 equations of equilibrium multiplied 300 total. Okay, so if you try to do that by hand, of course, it's going to take time. So sometimes, I usually don't do such a thing, but sometimes professors actually making students do a project. Okay, truss analysis software using MATLAB has that kind of thing. You can easily, well, it's not easy, but you can create something like that. Truss analysis software, which you type in number of joints, how many joints do you have, and you're going to sketch out the frame, and then software can solve simultaneously 300 equations, 300 unknowns. I mean, MATLAB can do such a thing easily. That's what the software is about, okay? But I'm not going to do that in this class. So I'm going to show you how to do truss analysis, and then concept is easy. I guess it's just redundant, so many things to be done. So let's just take a look. So we are going to talk about simple truss. That means non-simple truss. Do we have? Yes, we have non-simple truss, but we're not going to deal with it. So we are going to simplify everything, okay? Simple truss means the one key term here. We are going to assume that every truss is created by two force members only, okay? Structures of truss is made by only two force members. What is two force members? Do you remember that? Two force members. Two force members. Only two forces acting on a member. That's two force members. So that means truss is created by some kind of bar, metal bar typically, this kind of thing, with a variable length. So only two forces in the direction of axis of this bar is acting on it, okay? So if you pick up every member of a truss, it's two force member. So suppose if this is a joint A, this is a joint B. Force of A is equal to negative force of B. This is, by the way, if the force is applied like this, is this tensile or compressive? This is a compressive. On contrary, if you have a member of a truss, could be under this kind of force. This is called tensile. Remember, cables and ropes and wires and those things can only support tensile forces, okay? But trusses can support compressive force as well. Typically metal bar, okay? Now, important thing here, you are going to be given two methods, the method of joints and the method of sections. I'm going to ask you the question later after I complete this truss section. Which one do you like better? Do you like method of joints? Or do you like method of sections? Which one do you like better? I'm going to ask that question, so be ready to answer that. As I cover those materials, the answer is going to be, the heck, you know, are you joking? Of course this method. Your reaction is probably something like that. I'm not going to use one of those methods ever. This is nightmare. Yes. If I use method of, it's going to take 3 hours to solve the problem. If I use the other method, 30 minutes. Something like that. Then you need to understand why. Okay. Now, in order to do method sections, this is actually, okay, this is actually not the statics. This is actually a preview of solid mechanics. Actually, okay. Section means you're going to cut off the material, take a look at inside of what's going on of the material. That is actually do not belong to statics. Okay, it actually belongs to solid mechanics, in which ES202, you're going to take it after this class, solid mechanics. So method sections is actually, you know, sort of a sneak preview of solid mechanics. Okay, so I'm going to be very careful about that. All right, so having said that, this section is going to conclude with frames and machines. Wow, so that means after learning how to do method joints and sections of truss, you can actually analyze the real machine. The real machine may include this kind of thing. If I apply the force, oh, how much force is developed here, kind of thing. If I push everything down, how much reaction forces do you have on 3 tripods of X? Lots of things. Okay. If I try to push the speaker from the right-hand side, how much force is required to rip it open, so that I'm going to mess with IT kind of thing. Oh, because professor is so frustrated, he kicked that speaker and broke it. Now, how much force did he apply? You can set it down and do it your analysis and submit it to IT. Oh, this must be 20 pounds of force that this professor applied, because the screw here is materials, aluminum, something, and apply the shear force and ripping it open. The professor must be so upset against you, IT people. Kind of thing. Funny thing is, it may not be joking, I don't know. Okay. Simple truss. So let's just start with the simple truss. A truss, what is that? It is a structure composed of slender members, typically called a bar or something, right? So bar can take both compressive and tensile force. Okay. So you can apply both tension and compression forces for the bar, slender members. And then those members are joined together at their end points, typically 2 different kinds. One is a gusset plate. You know, if you go visit a construction site of a new home, you can see this kind of gusset plate all the time. Bolt or pin connection, like a 3 members connected with a pin. Now, the important thing is if you use bolt or pin, this is not going to prevent each member trying to rotate around it. Okay? So we're not going to have moment reaction. Suppose if you, even though you tighten up the bolts, still you can rotate around it. Okay? So that's quite important. So we are going to only look at the 2D planar trusses. In other words, only 2D. You can, of course, stretch it out to 3D analysis, of course. It is just an extension of 2D, okay? Now, this is a roof truss. like a typical house structure. This is a bridge truss, like a bridge, simple, like a mechanism here. So depending on the type of use, you're going to have a variety of external forces you have to support using the truss structure. So you can apply forces. Forces can only be applied at the joint. That's the truss. If you start applying the force in a member, something like this, this is no longer called the truss. This is called the frame or machine. We're going to take care of that later. Okay. So for a moment, as a truss being a simple truss, you're going to constrain yourself. External force and moments, of course, you can apply moments too. External force and moments applied only to the joint. Okay. All right. Go ahead.
Why is there no forces in the bottom, the roof truss?
Roof truss. What is?
There's two joints, but there's no any force.
There's no.
The two in the middle.
Two in the middle.
Down.
Down.
Yeah, those two joints.
Those two joints.
Yeah.
You can, of course, apply if you want.
Oh.
Yeah. It's just an example. Yeah. It just happened to be. Okay. All right. So there are two important assumptions. Number one, all loadings are applied at the joints, like I said. Okay, so we're not going to allow forces applied in the middle of a member. If a member's weight is to be included in the analysis, it is represented by vertical forces, 1/2 of the weight. For example, this thing has a weight, 1/2 of the weight applied at both ends. Okay. B, the members are joined together by smooth pins. So in other words, it's free to rotate around it. Okay. So there's no moment reaction at any location of joints. Okay. If we introduce those two simplification assumptions, automatically every member of the truss becomes two force members. Okay. Important. Two force members. So two force members include both tension or compression type of force supported for each truss. Okay. Next page. Important. This is very, very important. Okay. Now, if you do a poor job designing truss may be unstable. That means if you apply the force, it may collapse. You have to avoid it. In order to avoid it, at least minimally speaking, you have to create a triangular truss. Okay. For example, this truss is created by 4 members, A, B, B, C, C, D, D, A. But if you apply force P here, it is going to collapse it. In order to avoid it, you have to add member AC or member AD, either way, creating two triangular shape. Okay. Otherwise, the truss is considered unstable. This one, okay. This one's what? I'm not sure about this. So it looks like this is the minimum truss you have to create, probably. And then you can add, of course, 2 more members to form like a truss ADBC. Is that what I'm saying? Those two are the same thing, isn't it? No, it's not. I'm not sure about this figure. But anyways, the simplest form that is rigid is a triangular truss. Okay. All right, next page. So let's begin with the method of joints. As the name implies, you're going to basically take a look at one joint at a time, applying the force balance at each joint, trying to figure out what is the force developed for each member. That's called method of joints. Okay, 2 methods. One is method of joints. This is equilibrium of a joint of the truss, underlying the joint. So you're going to put your eye on each joint. Internal forces of the member becomes an external force on each joint. Let's just take a look at joint. So let's say you're looking at the joint B, okay? So this is the joint B. So joint B has 500 Newton external force applied at the joint B. 2 members creating joint B. Member BA is going to be replaced with force BA, tensile force. joint BC is replaced by force BC. This is compressive force, in which I really don't like this way. I oftentimes call this, okay, this is my method, okay? This is FCB. In other words, I try to be consistent with the direction of the force. If the force is tensile, that means force is from B to A, right? B to A. So that's why this is FBA. If the force is compressive, C to B. So that's why I usually call FCB. I don't like this expression, FCB. But by saying that, this is a compressive force, this is tensile force. Okay? So force is trying to pull this joint out. It's called tensile. The direction of the force is from B to A. So this is called FBA. This is a compressive force. The direction of the force is from C to B, FCB. Okay? So that's what I'm trying to kind of consistently trying to show. And then, of course, what can you do here? You can apply summation of the forces in X and Y direction. Is that right? You cannot do moment though.
Can it be the opposite? Like, is there any chance that FBA would be AB and would be compression, and then the other one would be tension?
If it's tension from B to A. So this notation actually indicates if it's compression or tension.
Yeah, but I mean, like,
yeah.
Can it be like just the opposite? Like the BC would be tension, and then the BA would be compression?
If you apply force this way, yes.
Oh.
Yeah, that's right.
Okay.
If you apply 500 Newton the other way.
Oh, because it has to balance it. Okay.
That's right, yeah. You can do that. But if you do such a thing, this is not pin support. It is going to fling it out. It's not the statics anymore. So that's actually improperly supported statics problem. So you can't do that. So in order to do that, you have to replace this with a pin support. This is a roller. Then apply the force this way. That means if you do that, this is compression, this is tensile. Right? Okay. Let's be careful about that. All right. So this is method of joints. Method of joints is going to be this. So you're going to apply summation of the force in X and Y direction at each joint. So you have two unknowns, FBA and FCB. You apply the force in X and Y direction, find out those two unknowns. Okay, now what's next? Let's move to the other joint. Apply force and moment X and Y. Suppose, if this is the problem, you have no problem. But suppose if you are dealing with the truss with the 2,000 joint points, you need the 2,000 equations. Each location, you need the two equations, 4,000 equations to deal with. How's that? So that's the 4,000 equations with 4,000 unknowns. It's a nightmare by doing by hand. Okay? So now you probably want to have a computer program to handle such a thing. This is called method of joints. Okay? Now let's just a sneak preview of, let's just take a look at the method of sections. So this section is quite important. So you're going to choose just about any location of the joint. You're trying to kind of virtually cut. Virtual cut. Okay? Virtual cut of the frame. And then find out internal force developed for that cut cross-section. This is called the method of sections. So obviously you have to cut the material and take a look at what's the internal force developed inside. This actually belongs to the solid mechanics, it's not statics, okay? Virtual cut. This is a sneak preview of solid mechanics. So let's say, for example, you are going to introduce a cut. Okay, virtually cut. Then what? Well, after you cut it, you can either pick up this component or pick up that component. Either one's fine. Okay, so this component or that component, of course, this one's easier. So I'm going to pick up this component. Here we go. So this is a joint B. This is the cut member BC. This is the cut member BA. Each develop internal forces. Important, internal. This is a two-force member. So if you cut just about anywhere, you're going to develop internal force, which is a uniform value, right? So this is a F, again, FCB, I prefer. FCB, compression force. This is FBA, tensile force developed. How on earth you can tell this is a tensile? Well, you have to think about one more step, okay? So let's say you just cut here, and also you just cut here and cut here too. Then pick up this member and that member and take a close look at it. So this member is going to look like this. So this is FBA, same and opposite FBA shows up, okay? This is also same and opposite FBA shows up. And this side is pin. Obviously, same and opposite FBA shows up. Okay? So think about that. Member AB. This much portion of member AB develops internal force FBA here. This is the portion of the member AB. That means this portion. Okay? Develop equal and opposite FBA so that if you put it back on, internal force cancels out. You have to cancel out internal force. If you put it back on the cut member, internal force must be equal and opposite, so it just cancels out. Okay? The other side, if you reconnect, maybe you just pick up a, I don't know, super glue and connect up. Equal and opposite FBA cancels out. So the original structure is, hey, here we go, resurrected. I just super glued it. So as you take a look at, this is tensile, isn't it? Because the portion of the member is trying to be stretched. It's a tensile. So when you get confused, you just picture yourself. You introduce cut, two cuts. You just pick up this component, but you can, of course, pick up this portion of the member AB. That's what it looks like. So this is tensile force developed inside. So this is the internal force tensile. This is quite important for solid mechanics because you need to understand this member is under tensile or compressive. This is going to be important information to determine internal stress. Internal stress, compressive or tensile? Which one is it? One is positive, one is negative. Okay, solid mechanics is going to be something like that. You have to cut, find out internal loading. Internal loading produces internal stress and then internal stress and then deformation and then internal strain. That is solid mechanics. Okay, and this is just a sneak preview. Any question here? So basically, this is the method of sections. You're going to pick up this, okay, then apply equation of equilibrium for this member. It's quite a bit different. This is the equation of equilibrium applied at the joint. This is member, okay? It's quite a bit different. You're going to see the difference soon enough, okay? Next page, page 5. This is actually one of the most important things before you start solving the truss problem. Now, the truss problem could be made up intentionally to confuse you. One of the techniques that I can use to confuse you is the truss, which actually I can add any member which is originally not really necessary to support the loading. It's called the zero force members. Let's just take a look at this example here. This is the truss. Okay. Some of the members are not really necessary because it doesn't support any loading. That's called zero force members. How can we determine such a thing? Let's just take a look. Truss analysis using the method of joints, especially method of joints. This is quite important. Method of sections, not quite, because method of sections, you can introduce just a cut just about any location. I can cut here, pick up this member or that member, apply summation of forces. You can do that, or I can cut here. I can cut anywhere. That's a method of sections. But if you stick with the method of joints, you are going to probably start from support reactions first, and then start from, okay, what about joint F? You have 1, 2, 3 force, and actually reaction force X and Y. Okay. Whoa, that is 1, 2, 3, 1, 2. Lots of unknowns. Oh my goodness. So I need another joint. Just this joint is 1, 2, 3, 4 forces. How about this joint? Oh, that's only 2 members. Summation of 4. Okay. Anyways, method of joints. This is quite important. You have to start with recognizing zero force members, because some of the members are not really necessary for this truss structure. So what are the zero force members? Zero force members support no loading. These zero force members are used only to increase the stability of the truss during the construction and to provide support if the applied loading is changed. C. The zero force members of a truss can generally be determined by inspection. Quite important. You have to determine by looking at it. So 2 methods, okay? This is quite important, 2 methods. Part A, if only 2 members form a truss joint and no external load or support reaction is applied to the joint, the members must be zero force members. What are those joints? Anybody? Please go ahead, try. If only 2 members form a truss joint and no external load or support reaction is applied to that joint, those 2 members are zero force members. What are those? Which joint?
A.
Joint A consists of only 2 members, right? Member AF, member AB. Member AF and member AB, 2 members form the joint A. And then joint A is not supported, so there's no support reaction, and there's no force applied at the joint A. So that means this and that are zero force members. You don't need those. Anything else?
Could we be able to D?
D. So this is a D. Member DE and member DC forms the joint D. And then no external force is applied on joint D. There's no support on joint D. You don't need this. So you can simplify this truss into this. This is what you needed. Okay? So you can massively simplify your analysis. So those 2 are essentially the same. You can simplify it. Before you start applying method of joints, okay? Or you start doing, okay, let's begin with joint D, and then let's apply summation of the forces at the joint D, and you realize, wait a second, FD is 0. FDC is 0, what the heck? Then you realize, hey, this is zero force members after you apply such an equation. Or, before you even start doing it, you can simplify it either way, okay? Here too. Obviously, joint A, you have FAF and FAB, summation of all the forces 0 in y direction. That means, hey, this must be 0. This also must be 0. Those two are 0 force members. You don't need that. Okay? Next page. So this is actually quite important. Okay? If 3 members form a truss joint for which 2 of the members are collinear, the third member is a 0 force member. Okay, so out of this, which joint is under such situation? 3 members create a joint. 2 of them are collinear. Which joint you're talking about?
C.
C, okay. So C, joint C is made up member DC, CB, and AC. Member DC and CB, those are collinear. So this is 0 force member. Is that it?
Then D.
Then D also. You're correct. So joint D is made up by member ED and DC. Those are collinear. So that means, hey, you don't need this. This is 0 force member. Here we go. You can simplify to here. Okay? So before you actually start doing your solution, you can eliminate 0 force members to begin with. Make your life much easier. Okay? Now, from the perspective of a professor, it's easy to create 0 force members. Make it look like, hey, this is a monster truss problem, but most of them are 0 force members. I can easily create such an example. Okay? And then you can use those 2 techniques to eliminate 0 force members. Okay? Any question? Let's move on. Take a look at example. Okay? All right, so this is page 7. Method of joints. Question is, do you like method of joints? Do you like method of joints? Let me be honest with you. I hate method of joints. I hate to death. I don't want to use method of joints. But anyways, I have to do it because I need to cover it. Okay? So this is a class example 361. Determine the force in each member of the truss in terms of the load P and state if the members are in tension or compression. This is quite frankly, if this is an exam, single problem consumes probably entire exam time, possibly. I can, of course, simply add, okay, well, let's add the 2 more members here. Oh, 2 more members here. Kind of thing, Those are 0 force members. But make it look like, my goodness, this is, okay? Anyways. One important aspect here is this is completely symmetrical. Okay, so as a matter of fact, you don't have to apply equations of equilibrium at all the joints. What you need to be doing is probably, first of all, you need to find out support reactions. Okay, that's the first step, of course. So you have to sketch everything and apply summation of the forces as a system to find out the support reactions to begin with. That's the first step. And then next step is, of course, go through joint by joint. But if you apply equation of equilibrium at the joint A, you're going to find out those 2. And then apply the equation of equilibrium here at the joint B, you're going to find out those 2. Using this as an unknown value. So starting from here, you can find out those 2, and then find those 2. That's it, because this is equal to that, this is equal to that, this is equal to that, because it's symmetric. If it's non-symmetric truss, of course, you have to do like one, two more. So 4 equations, each one of them includes equations of equilibrium in x and y direction. So total 8 equations involved, if so. In this case, this is symmetric. Your life is much easier. So let's just, first of all, let's do the entire truss, okay? So entire truss, I'm going to kind of quickly sketch the entire truss free body diagram. The purpose of doing this free body diagram of entire truss is, of course, you want to find out support reactions, okay? So, this is so thick, I don't know. Okay. So I'm going to carefully kind of sketch out. Okay, so this is, it looks like all lengths L right triangles, 3 of them. Okay. Joint A, B, C, D, E. External loading is applied at the joint E. The value is P. This is external loading. And then, of course, you're going to find out support reactions. This is pin support. So you have support reaction AY, support reaction AX, and support reaction here's DY. So first of all, let's find out those by applying summation of the force set equal to 0. So what is the first equation to apply? Of course, I'm going to apply summation of the force in x direction set equal to 0. This actually gives you very simply AX must be 0. Okay. So this is gone. This is 0. Next is, of course, I'm going to apply moment. I'm not going to apply force because if you apply summation of the force in y direction set equal to 0, you get one equation with 2 unknowns. You cannot solve it. So let's set the moment, summation of the moment at joint A. Let's set equal to 0. By doing so, AX, AY doesn't create any moment at the joint A. So force P is external loading, so creating negative moment. So this is going to be negative P times L plus dy times 2L. Is equal to 0. So this is going to solve dy straight out. Dy is, of course, half P. And then the rest is summation of the force in y direction set equal to 0. This is going to give you AY minus P plus half P. Half P's dy is equal to 0. This is going to give you AY is, of course, half P. So now you know the support reactions of A and D joints. Those are AY equal to half P. dy is also equal to half P. Of course, you kind of know it because this is a symmetric structure. So half of the P is going to support it at the joint A. Half of the P is also supported at joint D. Of course, it's kind of common sense. You can kind of tell. So this is the first step. Now you found support reactions. next step, now you're going to take a look at joint by joint. So I think my strategy is I want to find out. Okay. My strategy, okay? I want to find out internal loading developed on this member, that member to begin with by applying joint A equation of equilibrium is going to give you those two internal loadings. Next step is I want to find out this and that by applying summation of force and moments at the joint B after applying the joint A. Joint A is going to give you information of this member. That information is necessary to find out those two. Then once you find out those members, the rest of it is a symmetric, right? So you know the entire information. That's my strategy to begin with. So obviously, the very first step is joint A, okay? This is a method of joint. I hate to do that, but I have to do it. Joint A. Okay, so joint A is brought up here. So this is joint A. Now obviously, the force, FBA from B to A is applied here. And then you have half P. And then this is force FAE. Okay, three forces acting on joint A. Okay, so by doing I don't like this, but anyways, summation of the force in X direction, let's set this is a positive direction, let's set equal to 0. Okay. Do we know the angle here? What's this angle?
60 degrees.
60 degrees, because it's a right triangle. That's right. So negative of FBA cosine of 60 plus FAE is equal to 0. Well, this is the one equation with two unknowns. I don't like it, but let's keep it as it is. This is equation 1 I got. Now, next is summation of force in Y direction. Let's say this is a positive Y, set equal to 0. Okay? This is half of P minus FBA sine 60 is equal to 0. Well, this is actually single unknown, FBA. This actually gives you FBA. Oh, that's good. So this actually gives you FBA is equal to half of P divided by sine 60. If you do such computation, this should be 0.577 P. Well, now we know FBA. And then this information is going to be plugged back into equation 1. If you plug in FBA is equal to 0.577 P, FAE is equal to FAE is equal to 0.5 times 0.577 P. which is 0.289p. Now we got information of member BA and member AE. You got those two figured out. Next step is, of course, you're going to look at joint B. Okay. So now you're going to draw joint B here. Now for this joint, you have a force from the member CB. This is FCB. And this is a known information from joint A. This is FBA, or in this case, FAB. In which this is 0.577p. Okay? FAB is equal to FBA, 0.577p. We know that information from joint A. Okay? Also another member here. This is FBE. And then we do know this is 60 degrees. And this is also 60 degrees. Okay. So once again, you're going to apply summation of the force in x direction set equal to 0. Okay. This is going to give you 0.577p cosine of 60 plus FBE cosine of 60 minus FCB must be set equal to 0. Let's just simplify a little bit. This equation is simplified a little bit. FCB is equal to 0.289p plus 0.5 FBE. Again, this is one equation with two unknown. Let's just set this equation. Let's call this equation 2. Okay. Next is summation of the force in y direction set equal to 0. This is going to be 0.577p sine 60 minus FBE sine 60 is equal to 0. From here, you can get FBE, which is equal to 0.577p. So now we got FBE. Let's just plug in this information into equation 2. You get FCB. Okay, FCB is equal to 0.289p minus 0.5 but minus, plus, isn't it? Plus, sorry, plus. Plus 0.5 times 0.577p. You got FCV is equal to what? 0.577p. It looks like it's either 0.577 or 0.289p. Okay, it looks like. Now, you can say FCD as a symmetric. This is equal to FAB, which is 0.577p. You can also say FDE as a symmetric. This is equal to FAE, which is 0.289p. You can also say FCE is equal to FBE, in which 0.577p. You can say those things because it's symmetrical structure. Symmetric in terms of both structure and also loading. Loading is only P applied in the center. So it's completely symmetric. So this is a special case. Usually, you can never do such a thing. Suppose if I change my mind and apply force P in here, all of a sudden you can never say those things. You have to apply, okay, so what's the next joint? Joint to C, joint to E, joint, well, you have to do all of those joints. All of a sudden. Do you write this method? The hell no, right? I hate this, but you have to do it. This is a joint method of joints. Go ahead.
For joint A and joint B, how did you determine which way the forces were going to be applied?
Usually by observation. In other words, suppose if create this kind of truss, if you apply the force this way, this is stretch, this is compression, sort of. You can tell by looking at observation. But if you have no clue, you can basically determine based on your guess. Then the answer might come up with negative value. Then at that point, hey, wait a minute, my initial assumption is wrong. Let's flip-flop the direction. That's what you need to do.
Okay.
Yeah. So either will work fine, but I usually don't want to flip-flop at the end. So I kind of start with my own observation using common sense. Okay. So this member seems to be stretched out because the direction is this way. This member, well, I have to support this way. So this is compressive. I guess we did that discussion with you,
yeah.
Right? Yeah, that's a common sense-based analysis. Obviously, you have no clue. Okay, let's just assume this way. Then ended up having negative, but okay, negative value. Force is this way. You can do that. Okay. Do you have any question here? So this is very, very, very simple. Symmetric truss. Still, you need a full solution for full page. Imagine this is non-symmetric truss. I can add 2 more members for each size. Oh my goodness, this is very quickly nightmare problem. Truss is not easy. Well, I mean, actually, it's easy in concept, but it may end up having tons of complications involved. That's the truss. Okay. So you need to be efficient. In other words, first of all, zero force member, let's just remove it. Number 2, when you apply equations of equilibrium, let's just be very carefully apply in order so that you can eliminate as much as unknowns for each problem, each equation, so that you can get answer straight out kind of application. So moment equation applied first. Usually, that's going to give you 1 unknown force coming straight out of that equation. The other 2, just a program check coming up with 2 reactions. So strategy is quite important. Okay. And also, you can sort of observe that you can predict, hey, this must be tensile, this must be compressive. You can say that before you even apply the direction of the force at each joint. Okay. So quite a few important things. Okay. So next page is our homework. Oh. Holy cow. Homework 361. Determine the force in each member of the truss and state if the members are in tension or compression. Assume each joint as a pin. Although this is gusset plate, it's a pin. P is 4 kilonewton. Okay, so this is the same exact procedure. First of all, you have to find out support reactions at the C and D. 2 unknowns in C, 1 unknown in D. Support reactions. Okay, and after that, you're going to start from, okay, well, I'm going to probably start with maybe A. A is two members creating joint A, one external force P applied. So you can determine AB and AE. That's the first step. The next is using that information, you just joint B. That is going to create the BEBC information. And next is joint E. It's going to find out EC and AD. And then joint C. And then lastly, joint D. How many equations? 1, 2, 3, 4, 5. 5 times 2. 10 equations, probably at least. Okay. Now, you understand that each joint, you are not going to apply summation of the moment at that joint set equal to 0. That cannot be done. That cannot be done. Do you understand that? Because all the forces acting into the joint. Summation of all the moment at that joint is 0 equal to 0. There's no information you can squeeze out by applying moment summation at each joint, of course. You know that, do you? So the only equation available at each joint is summation in force in x and y direction set equal to 0 at each joint. Now, at the very beginning, when you try to find out support reactions, of course, you can apply sum of the moment at each location is 0. Of course, we can do that because that's a support reaction. But each joint, summation of moment set equal to 0, of course. All the forces acting on that joint, no moment. So that equation is quite frankly, it's not effective. You cannot use it. Okay. So you may end up having 10 equations to solve this problem. Method of joints. Like I said, I hate to death about method of joints. Everybody hates method of joints. Not because it's difficult, no, because it is redundant. You need lots of equations to solve everything. That's why. Okay? But this is homework, too bad. I don't think you can finish in single page. You probably need at least 2 pages. Okay? Just to use flip side of the worksheet and finish up, or do it in very, very small, tiny drawings. Okay. Next page. Class example 362. Do I have time for that? Yeah, let me just try to finish it for this today. Class example 362. A sign is subjected to a wind loading that exerts a horizontal force of 300 pounds on joints B and C of one of the side supporting trusses. Have you ever seen this kind of sign? Not sure. Determine the force in each member of the truss and state if the members are in tension or compression. Okay. Actually, did I state tension compression in previous? Perhaps not, because I kind of knew this is compression tensile. So if you have a positive sign, FBA is, of course, this is this tensile or compression? Tensile, yeah. This is tensile, right? It's kind of misleading because, wait, if BA is pushing into the joint A, isn't this compressive? No, this is tensile. Once again, you have to be very careful. This is what's going on. Right? Wait a minute. Compressive, is it? Yeah, I always kind of confused that with. So this is the pin. If you disassemble it, so this is the pin, so you disassemble it. FBA, is FBA tensile? Isn't that compressive? Because if you disassemble something like that, so this is compressive, isn't it?
But on joint B, we have it going the other way.
This is
So,
compressive.
Like, looks like it.
Yeah. So AB is compressive. Yeah. A is tensile, right? A is tensile. In other words, AE is going to be like this. If you disassemble, it's going to be like this. So it's tensile. So FA is tensile, FB is compressive. Is that correct? Make sense?
Yeah, I have a question.
Yeah.
So like on joint A, we
Yeah.
have FB going towards the joint on A, but in joint B, we have it going up towards the joint on B. So wouldn't it have to be tensile?
Yeah, that's what I'm thinking too. Although AY is reaction force. So reaction force is sort of pushing this member AB up. So it seems ended up having compressive force developed in this member because P is trying to drag it down the entire member. This is kind of resistive against it. So as a result, sort of this member is under compressive. Again, it's based on observation, but that's what's happening. Okay. Good point, though. Although oftentimes you can never tell sometimes if this member is compressive or tensile. So you just basically guess it. Then if you get, well, negative sign comes out, well, yeah, well, of course, this is a free problem. You can always correct it with after you complete your equation of equilibrium at each joint. I thought originally FAB is this way, but well, this is a negative sign. That means, hey, this is actually the direction. You can do that always. Okay. So this is compressive, obviously. So FBA is compressive, FA is tensile, FCB is compressive, B is tensile. Okay. So you can tell all of those things. Okay. So let me just finish up by saying tensile or compressive. Okay. So FBA, this is compressive, C. FA is tensile, T. Okay. FBE is tensile, T. FCB is compressive, C. So FAB is so this is compressive. FDE is AE. This is tensile. FCE is BE, tensile. Okay, so please don't forget as you try to solve the homework assignment, each one of those internal loading developed for each member, you have to specify either compressive or tensile clearly. Okay. So put C or T within the parentheses saying this is compressive force with this magnitude. This is tensile force with this magnitude. Okay. Now, obviously, you may end up having, originally you thought FBA is tensile force and then ended up having negative sign in front. If so, you're going to say, hey, FBA is actually, I thought it was tensile, but it's actually compressive with this magnitude. You can say that. Okay. Yeah.
So, okay,
Yeah.
So I was thinking about it more for FBA.
FBA.
when you do up, wouldn't it have to create a tension between A and B in order to maintain stability? So would it be compressed or compressive? Because I'm confused how it would be compressive instead of tensile.
Tensile means you need to have some kind of a force trying to continuously pull this member upwards, isn't it? There's no such a thing. That's one thing, right? It could be BC is if the BC is tensile. In other words, this member is continuously pulling this member AB. It could be tensile, but BC, as you see, BC is compressive. So this is compressive, and then BE is tensile. So this is tensile. In other words, this member is tensile. So this member is kind of trying to stretch it, but member BC is compressive. So this is compressive. I don't know why. Is it going to balance up here? Joint B. This is a yeah, so this is FAB is what? FAB is compressive, isn't it? FB is compressive, so this actually supports the joint to be from here. So this member being compressive means this member seems to be this, and then this is what's happening at the joint A. And joint B, this is happening, right? That's what the compressive member means. Okay.
If you say that
yeah,
the force pushes joint A.
Force pushes joint A. Yeah.
Like the BA.
That's AY. AY is actually pushing joint A up, but member AB is trying to resist it by producing compressive internal loading.
But if it tries to resist it, it's supposed to be towards point A. Like you.
Yeah, towards point A. That's right.
So how in the
this is a member. Yeah, suppose you introduce your cut here. Take a look at the portion of the member AB. This is compressive, isn't it? This is a compressive. So this is the member AB being cut here.
Yeah, but like, why did you draw the arrows exactly the opposite from the member, from the joint?
Joint is this, FBA. This is FBA.
Yeah.
Yeah.
So then
equal and opposite, because this is cut. But if you cut budgetary, you have to create equal and opposite force shows up at the cut cross section.
Oh.
Because if you glue it up again, those forces must cancel each other.
Oh.
Right? That's the internal force. Again, solid mechanics idea. So those two are equal and opposite. Those two are equal and opposite. Because this is just a budget cut. If you assemble again, forces cancel each other. Go back to the original configuration. That's internal force. So internal force, if you look at internal force of member AB, this is compressive. That's what it is. So this is clearly compressive force developed for the member AB. You know, it's kind of confusing, but I hope it makes sense. You have to take a look at what's inside of each member, because that's what it is. That's what we're trying to find it. That is equal and opposite to the force applied to each joint, which is actually making you kind of confusing. So, right. So this is going to be more clear if you look at the method of sections, because we're going to introduce cuts, okay? So I oftentimes, I kind of feel, wait a minute, isn't that opposite? If you look at the joint, of course, joint is external force. After you disassemble the member, it's going to be an external force. But if you internally cut, this is internal loading, which is equal in the opposite direction. Okay. All right. Okay, great questions. That's one of those things I was kind kind of confused too when I was a student. And then I don't think I can do this problem, but let's just take care of one thing. Do you have a zero force member for this structure? Let's just take care of it. Do you have a zero force member?
D.
This joint to D is created by member CD, member DE, member BD. This is collinear. That means, hey, this is zero force member. Okay, because it's collinear. So you don't need member BD. So when you try to analyze, you just completely ignore that. Okay, you just remove this member BD to begin with. So we are going to pick up from this page, page 9, tomorrow, and then continue doing trust analysis. Do you have any question? Let's stop here today. Have a good day. Okay. And then, like I said, tomorrow is a homework due. Homework 2B. Right. Homework 2B is due tomorrow. Homework is due today. Sorry, you turned in homework already. And then tomorrow is what? Quiz. Yeah. So I'm going to post the solution of the homework today, right after I go back to my office. So please take a look and then double check your work. Be ready for the quiz tomorrow. Any question? Have a good day. All right, see you guys tomorrow.